Differential equation is a equation in which it relates the differential form of a certain function with its own function in itself. And differential functions could be solved in multiple ways, but in here we'll be focusing lots on homogeneous differential equations, and we will discuss about ordinary differential equations until partial differential equations. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire video. So in here, I want to display all of the things that we'll be discussing throughout this entire video. So first, we'll be discussing about the introduction, a little bit about the theory behind differential equations first. And then after that, we'll be discussing about ordinary differential equation with constant coefficients. And this is one of the easiest types of differential equations that you could solve. After that, we'll be discussing about first order ODE, or ordinary differential equation. After that, we'll be discussing about second order differential equation, in which we'll be only discussing about the homogeneous types. Finally, we'll be discussing about partial differential equation, and then we'll later talk about the Green's function method, in which this is a very advanced method for you to solve a differential equation. Green's function method. So here are the timestamps for the discussion, and so you could skip through just in case if you want much more study for these particular topics. So let's talk about what is a differential equation in the first place. So a differential equation is like I said, if you have a function, let's say v, in which it is related by another function. So let's say it's d squared v over dt squared plus omega squared omega squared v is equal to 0. This is what we call as a differential equation, since it is relating a derivative with the original function. And there are lots more of these equations, in which I will display some of them in here. So the top one here is something which is very popular. This is what we call as the harmonic equation, but there are more of these. For example, the wave equation, it's 1 over v squared of partial squared psi over partial t squared minus the partial squared psi over partial x squared is equal to 0. This is the wave equation. You also have another type of equation, which is something that you observe when you're dealing with a pendulum, which is something which you call as the sine Gordon, which is 1 over v squared partial squared psi over partial t squared minus partial squared psi over partial x squared plus sine of psi equals to 0. This is what we call the sine Gordon. And sorry, this is not really within a pendulum, but this is a type of wave equation in which it also exists a function with respect to the sine of psi. So these three equations that I show you here, you could categorize them into different types. So first you have something which you call as the ordinary differential equation and a partial differential equation. A partial differential equation involves partial derivatives, while ordinary differential equations only deals with exact derivatives. So something like the harmonic equation is an ODE, the wave equation and the sine Gordon is a PDE. And so the way for you to solve an ODE and a PDE is different, but they are related to each other. Another thing to discuss about is the linearity. So a function is linear if it follows the rules of linearity, in which AF plus BG is still a solution, in which it means that if you have a constant as well as a coefficient, you could just sum them all up depending on the coefficients, and this will construct your equation. So something like the harmonic wave equation, in which the v and the partial squared v over partial t squared are independent of each other, and the coefficient in here is just omega squared, this is linear. Same thing for the PDE, for the wave equation, it's also linear, but the sine Gordon is not linear because there's the sine psi, which is not really one of the constants or the variables that we are interested in. So this is nonlinear. Nonlinear. Another thing to talk about is the order of the differential equation. So the order corresponds to the highest derivative of the equation. So all of the things here are second order. They are all second order differential equations. And lastly, that I would normally talk about is about the homogeneous differential equation and a heterogeneous differential equation, in which I won't fully discuss about it now, but it is related to a linear differential equation. So let's look at the property of a linear differential equation. So let's say if you have some form of a operator. Let's say the wave equation d squared v over dt squared plus omega squared v is 0. The question is, if I have another function, let's say this is solved with v1. So if v1 solves this problem, is a v1 also a solution of this problem? And so if you put it in straight away, let's say a is a constant. If you put it in, you would get the ad squared v over dt squared plus a omega squared of v equals to 0, which is the same thing as d squared v over dt squared plus omega squared v equals to 0. So it turns out that this new v2 here is also a solution of the differential equation. And also alongside with that, if let's say v1 and v2 are pretty much independent of each other, the question is, if v1 is a solution and v2 is a solution, is v1 plus v2 a solution as well? So we could do the same thing. So we'll get d squared v1 over dt squared plus omega squared v1 plus d squared v2 over dt squared plus omega squared v2 equals to 0. So what we observe is that if you have a independent solution and another independent solution, the linear combination of those two things will also follow this differential equation, as long as it's homogeneous. But what about if it is heterogeneous? So homogeneous corresponds to the equation equaling to 0, but for a heterogeneous, it's normally written as something like this, plus omega squared v plus, let's say, a function f, which is a function of t, let's say. The question is, if I have v1 and v2, are they solutions of this differential equation? Let's just use the same type of equation that we got. So if we use the same solution, it would result into a 0, right? And so there should be another solution, which in here I will just write it as v3. v3 is a solution of this differential equation. Let's say something like this: d squared v over dt squared. But let's say the rest corresponds to this type of equation. So v1 and v2 are from here. And so what you would gain from this information is that you could get v1 plus v2 plus v3 is the solution of this differential equation. So you could split up your differential equation into the homogeneous part and the heterogeneous part. So we have covered the entire basics as well as the categories of differential equations. So now let's talk about the ordinary differential equation with constant coefficients. Constant coefficients. So let's just do a very simple example. dx over dt is v, in which v is a constant. So this is like velocity. So if we observe this straight away, we could solve this by any type of methods. In here, I will be introducing a method which you call as separation of variables. So you just group all of the functions of x and the functions of t on the other side. So you could get dx equals to v dt. And then integrating both sides would give you x equals to vt plus the integration constant c. This is how you do the method of just splitting it into different variables. So You separate the variables into one side and the other variables into the other side. So what you observe here is that the C here corresponds to a constant in which it is contributing from the initial condition. So a differential equation you normally encounter a initial condition problem in which you are given a initial condition. And this is very important since integrating gives you this plus C, and this plus C is solved from this initial condition. Let's do another example. Let's do the second order but constant is equal to A. This is normally what we observe when we talk about gravity, let's say. Let's say it's negative G. Let's just do a much more physical problem in which the acceleration is going downwards at a force of G, 9.8, let's say. So if you do this type of ordinary differential equation, you could do the separation of variables, but separation of variables in here doesn't really make sense because you would need to do the d of dy over dt, right? And so in here, I want to introduce a method that I normally use if you don't know about doing the separation of variables straight away. So let's just call dy over dt our v. So we could now separate our differential equation into the dv over dt equals to negative g, and then after that, dy over dt is v. And so you could solve each of these differential equations. So from the top side here, we could get your v to be gt plus c, in which c is a integration constant. And so after that, you could do dy over dt equals to negative gt plus c. Now this is also a differential equation. Now using the separation of variable, you would multiply both sides by dt. So dy equals to negative gt plus c, integrate everything. Multiply everything by the dt. Now if you integrate both sides, what you would get is negative g over 2t squared plus ct plus d, in which d is also a integration constant. So from here, what we observe is that there are two constants which is governed by two different initial conditions. Let's say position as well as the velocity in here. So if you now start to look at this problem, you could state that if you have a function, let's say d to the power of n equals to d to the power of n of x equals to a constant, let's say a, you could just solve the problem and you would need to have n different integration constants or initial conditions. Now let's talk about a problem in which we have already discussed, the harmonic equation. So let's write the harmonic equation. D squared x over dt squared equals to, plus omega squared x equals to 0. You could do this by the method of separation of variable, in which I have discussed a bit, or you could just do it with a matrix method. So I will do the matrix method because it makes a little bit much more sense, especially if you're starting with it. But you could also do a method in which you just guess the solution. So let's just show you how I will do this in the matrix form. So we would just start by writing, let's say, dx over dt is y. So you would get the differential equation to be dy over dt plus omega squared omega squared x equals to 0. And then also dx over dt minus y is 0. So if you remember about how we do simultaneous differential equation from the matrix video or the linear vector space, what you would do is that you would write this in terms of the matrices. So you would get x dot and y dot here, and its relation with x and y. So if you fill in the space, this would be 0, 1, and then at the bottom, this would be negative omega squared 0. Now, if you remember from the linear vector space idea, you just do the eigenvalue, and then it will later help you solve this differential equation. So let's just do that method. So let's just straight away try to find this eigenvalue problem, we'll just transform this into another type of matrix. So if you observe this guy's eigenvalue problem, let's say the eigenvalue is lambda, would be lambda xy. Let's just do it like that. You just need to find the certain type of xy's or the linear vector space for you to convert it. So you could just do this, do the do the uh do the eigenvalue problem, and this would solve into lambda squared plus omega squared equals to 0. There we go. And so this would solve into your lambda to be plus or minus I of omega. Now this means that you would get your differential equation to be something like this. X dot and y dot here, and this would equal to, sorry, so we'll just transform this into our new coordinates. So x1 and x2. We'll just use these two new coordinates. So it will be I omega and negative I omega, corresponding to each of the eigenvalues, and then you would get the components in x1 and x2. So now, observing this, you would know that this would mean that x1 dot equals to I omega x1. And so if you do this by the separation of variable again, this would be the dx1 over x1 will equal to I omega dt, which means this would be the natural log of x1 equaling I omega t plus c, which means x1 would equal to e to the power of I omega t, multiply this by a. Same thing for x2, but instead it's a negative, the e to the power negative I omega t. Now, these two solutions would form the entire solutions of the differential equation. So you could write this as a e to the power I omega t plus b e to the power negative I omega t is a solution of the differential equation of the harmonic equation. So you could also guess the solution. It's just cosine omega t and sine omega t, and then just plug in all of the integration constants based on the initial conditions. So there are some uses of the differential equation. One of them is on the Lagrangian mechanics, in which I won't fully discuss much in here, but the Lagrangian mechanics will later be discussed on classical mechanics, in which I'm planning to teach about. So Lagrangian mechanics is a method for you to solve mechanics, but instead of looking at the change of position or pretty much the forces, you instead look at the differential form, or something which you normally call as the action. So the action in here is a physical quantity that describes how much action that you need to perform such action. It's literally just that. And so the action is defined to be the integral from the first time to the second time of the energies, of the kinetic energy to be precise. So you got the translational kinetic energy and as well as the rotational kinetic energy. This is the action. So I won't fully discuss much about this, but you would see that there's this x dot, there's this x, and it's pretty much just a differential equation. So let's try to discuss about the linear differential equation again. So you could express a linear differential equation or a homogeneous one just by writing it as the sum of the constants aj of dj, which is the operator, the differential operator operating on x, is equal to 0. This is the property of a homogeneous equation. Now, almost every single differential equation which is homogeneous and has constant coefficients would have a solution in terms of ae to the power of alpha t. And so if you know ae to the power alpha t, you could solve for the alpha straight away. So it could be written as the sum of aj alpha to the power of j plus 2 equal to 0. This is the condition because x is going to be 0. And so if you put x equals to a e to the power alpha t, and then you do all the derivatives, you can just extract off the a e to the power alpha t outside, and you would get this. And this is a very elegant way for you to solve some of the general solutions. And also because of this is just a polynomial. So if you know the factors of the polynomial, you know all of the alphas straight away. And each of these alphas will correspond to a linear independent solution. So if you combine all of them into one, you would get the general solution. But let's consider some examples. We could try to consider if there are degenerate cases in which instead you would have alpha 1 and alpha 2 to be the same, let's say. So if there is this type of situation, we could just do, let's say, we could just try to observe if these two alphas are very close together, but they are still separate. So maybe one of them is e to the power alpha 1 and the other one is e alpha 2. And remember about and now if you remember about the linearity, if you take the linear combinations of these two, in which I'll just do it in this form, let's just do it like this would still be a solution. Now, if you take the limit as the alpha 2 goes to alpha 1, what you would get is this entire equation becomes e to the power alpha 2 of alpha 1 minus alpha 2 dt. Well, you know what? Let's just reverse the order. Something like this, minus e to the power alpha 2 t over alpha 1 minus alpha 2. And this could be denoted as the delta alpha. This thing could also be written as the delta alpha. And so this is just pretty much the derivative with respect to alpha of e to the power alpha t. So another type of solutions of this is t e to the power alpha t. And this is a solution if there's degenerate case. Something like, let's say, if you got d squared x plus 2dx plus x equals to 0, you might need this type of solution for it to solve the problem. So let's do an example of how do you use these methods of e to the power alpha t. So let's just do a problem in which if you have a mass and spring, then you also have a dampener as well. Dampener, something like this. So the differential equation, I won't fully prove this. It's negative kx minus 2m gamma x dot equals to mx double dot. So solving this would just become x double dot plus 2 gamma x dot plus the omega squared of x. So we'll just denote the m over k to be omega squared, which is something that we normally do in physics. So if we try to solve this differential equation, you could just straight away guess e to the power alpha t, a e to the power alpha t, and then just do it straight away. And what you would observe is this would become alpha squared of a e to the power alpha t plus 2a gamma alpha e to the power alpha t plus omega squared a e to the power alpha t equals to 0. Now to make this special, we don't want a to be equal to 0, so we could just divide everything by a. And also e to the power alpha t is never 0, so we could just divide everything by e to the power alpha t as well. So you would get alpha squared plus 2 gamma alpha plus omega squared is equal to 0. Now if you solve for the if you solve for the alphas, you would get negative gamma plus or minus the square root of gamma squared minus 4 omega squared. Now this is where the role of knowing imaginary numbers comes in. So if you have gamma squared minus 4 omega squared to be greater than 0, which means that the square root would be real, it would form into two different types of equations. So we will be assuming that in here the gamma is greater than 0 and the omega is greater than 0. What we observe from this relation is that is that you couldn't have this alpha to be greater than 0. It turns out that if the gamma squared minus 4 omega squared is greater than 0, the negative gamma plus or minus the square root of gamma squared minus 4 omega squared, especially when gamma and omega is greater than 0, wouldn't impose it to be a positive number. So it would be two different decaying functions. You would get a e to the power alpha 1t plus b e to the power alpha 2t. And each of them are decaying, something like this. And so if you take the linear combination of this, it could be something like this, in which this is the solution of the spring damp system. Another type of condition is if the gamma squared minus minus 4 omega squared is less than 0. This would conclude that your square root will become a imaginary number, and thus what you would get is a e to the power of negative gamma t, which is a component that decays, and also the imaginary parts, in which I will just denote this imaginary part. Oh, sorry, there shouldn't be any negative 4 here. Something like this. So if we observe this again, what you would get is that there will be two different components in the imaginary parts. And if you know how do you convert this imaginary parts into sines and cosines and just taking the real part, you could get the a cosine of the square root of omega squared minus gamma squared t plus b sine the square root of omega squared minus gamma squared t. I'll just leave this as an exercise for you to solve. But what this tells you is that this is a decaying function as well as a sinusoidal function that is decaying over time. So you would see something like this. But there's a final condition in which gamma squared minus omega squared is 0. When this is the case, you would know that the root will repeat. So alpha 1 will be alpha 2. Alpha 1 will equal to alpha 2, which means that this would resolve into two different types of equations. First of all, you know a e to the power alpha t is a solution, but also so this is technically negative gamma if you know about the equation anyways. But the second one will be another equation, which is the bt of e to the power negative gamma t. And so this could be simplified further into a plus bt. And this is the solution, this is the final solution, in which we call this solution as a critically damped solution. But sometimes you don't always get a homogeneous function in physics. Instead, you could get the equation which is heterogeneous, in which there's this f. So let's say it's the sum of an d of n of x. Now let's use a very specific solution of this f. Let's say it's f e to the power I omega t, something like this, in which it's a sinusoidal. You could guess the solution straight away, or in here you could just observe that e to the power I omega t, if you just put this value in, the e to the power I omega t will later destroy itself. So what you would have is a constant f, which is very useful for you to know. So you could just take this as something like this. I omega n of the a e to the power I omega t equals to f e to the power I omega t. So you could just cancel these guys out. And what you would need to solve is literally just this equation here. So if you solve this equation, it's just a equals to f over the sum of a n I omega n, I omega to the power of n. But let's consider a very specific solution. So maybe let's just say that it turns out that it's alpha n t. So it turns out that this is a factor in the nth term of your polynomial. So you could just also write your equation as alpha. Sorry. You could just write the differential equation as d minus alpha 1, d minus alpha 2, and so on, right? Until alpha n. And so if you try to solve it, if you have the factor to be one of the factors of the function, what you would need to observe is this. D minus alpha n, if you take a e to the power of alpha n, what do you observe? You would get alpha n minus alpha n, right? So it's a alpha n and alpha n, right? Which is a very bad thing because this would equal to 0, which means that your a would be a value that is approaching to infinity. So let's just assume a is a function. Let's just assume that instead. You would get dA, and you would get the alpha n to be outside, e to power alpha n. Well, first you would have this guy plus the alpha n of e to the power alpha n, so it's the derivative of the alpha n, and you would get the a still free. You subtract this by the alpha n, a e to the power alpha n t, and this turns out that this would equal to the dA of e to the power alpha n. Now this gives you a very good clue. So if you get d minus 1 alpha 1, d minus 2 alpha 2, and so on, for x equals to f equals to e to the power alpha n t, and if you just guess the solution of a e to the power alpha n t, assuming that a is a function instead, you would get this simplified into d minus alpha 1, d minus alpha 2 until the n minus 1, and then at the nth term it would become e to the power of alpha n of dA and t, sorry. It's equal to fe to the power alpha n t. So now you could just cross off the e, so you could just put the e to the power alpha n t and then just assume that dA is a constant. We'll just assume this to be a constant now. So what you do now is that you'd get all of these terms on the outside here, like so, right? Alpha 2 and so on. And then you would get the e to the power alpha n to be cancelled out, and you would get the dA. And this would equal to fe to the power alpha n t. No, sorry, f. So you could now solve what is your dA, which is just a constant. Alpha n minus alpha 1. So it's just a product of this guy. And so you could get what your a is, which is just the f over the product of alpha n minus alpha 1 plus a integrating constant plus c again. And so you could just assume this to be 0 because this would later be repeated on your general solution. So what we did previously was that we solved for the particular solution. So the particular solution is pretty much just one solution that solves for the heterogeneous solution. And you would also have the homogeneous solution. The homogeneous solution solves for the homogeneous case. And the sum of these two will be the general solution. And why is that the case? Let me just show it to you straight away. If you just have this equal to, let's say, f, and this equal to 0, if you sum them both up, because of the linearity, the solution of one must be the linear combination of the others. This is very important. So you could just do a linear combination of your homogeneous solution and it would still work. So what I discussed here was only by using exponentials, right? But obviously that the right hand side could be a function of, let's say, x. So how do you do that? Well, you have already studied about the Fourier transform and the Fourier series. If you use those two informations, you could solve for any type of functions as long as you could just transform it into the Fourier series or the transform, and obviously I think the series would be better for this. And if you sum up of this series, you would get the general solution that you could just put for your particular solution. You could also obviously guess the solution, which is also a viable option, but I want to highlight the way for you to do this in general. So as an exercise, you could just try to do this type of differential equation, but instead make it into a Fourier series of, let's say, the f equals to x. Let's go and discuss about ordinary differential equations of the fourth order. So ODE of first order. ODE first order. Now, let's just do a homogeneous solution first. dy over dx plus a polynomial y equals to 0. If you do the separation of variables, you could just do this as dy over y equals to the negative p of x dx, right? So this would solve into natural log of y equals to the negative integral of the px dx. And so your y would be the e to the power of negative integral of px dx. So okay, that's pretty easy. But let's now start to consider about dy over dx equals to the px y equals to qx. Now this is a little bit much more complicated. But let's try to remember of the linearity of a differential equation. Instead, let's just try to use the same solution, but let's just add a coefficient at the front of this. So obviously, if you do the first problem, there obviously is a first there is the integration constant hidden. And so now if you do this again, but instead let's just assume that a is a function. If you do the same integral, what you would get is this. So you would get the dA over dx plus the, and so you would also get the y1, let's say, the y1, which is the guess. So we'll just have y2 equals to a function of y1. We'd get that plus the a of the dy1 over dx plus the p of x y1 equals to q of x. Now, if you remember, this thing here results in the 0, which we have already solved. So we could just do the problem of dA over dx, y1 equals to qx. And y1 is a function of x, okay? So we could now solve this much more easier. So now solving this problem, you could get the dA over dx equaling to the q of x of e to the power of the integral of a qx. Okay? So, no, sorry, this is p of x dx. And now you could get what your a is. So you could get your a to be the integral of qx e to the power of integral of px dx dx. And this is literally just the solution. You could just substitute this back into the top side here, and you would get the solution. So let's just do a very simple example of this. So if we have dy over dx plus xy equals to x, let's say, the way that you could solve this is, obviously you could just do it by separation of variable. If you do it cleverly, you could just make this into dy over dx equals to x1 minus y. And so you would get dy over 1 minus y equals to x dx. Or this is just the natural log of 1 minus y, the negative, I think, equaling to the x squared over 2. And so what you would expect the solution to be is 1 minus y equaling e to the power negative x squared over 2. So your y would be 1 minus e to the power negative x squared over 2. Technically, oh, well, there's plus c, so a there. So yeah, something like this. So this is the guess of the solution that you could do from separation of variables straight away. But not all of the functions that you would do is this simple. So let's just use the method that I give. So let's just find out what the guessing solution, e to the power negative x squared over 2. Is a very good solution that we could use. So we just need to figure out what's the a. So your a would be the dA over dx would be the q of x, which is x, and then the solution that you got, e to the power of x squared over 2. So it's the negative power because you're just doing the reciprocal. So it's divided by the y1. And this thing is pretty much e to the power of x squared over 2, I think. Yeah. So your a is e to the power of x squared over 2. So this gives you the solutions of the problem. So one of the solution is 1, the other one is just a e to the power x squared negative x squared over 2, which comes from the integration constant again. So it's like e, this guy plus c. So there's this other constant in here that gives you the initial condition problem. So that's how you solve a first order differential equation in general, a homogeneous first order differential equation, or a heterogeneous one. Another set of the first order differential equation wouldn't really come up when it is linear. It might seem nonlinear at first, but it is linear, it turns out. So this is what we call as the Bernoulli's equation. The Bernoulli's equation. And it's very clever. So let me show you the equation. Take the derivative of y, and then you add it with the p of x of y. So this is just the first order stuff. But this equals to something that is not linear. Let's say q of x of y to the power of m. Now this doesn't seem to be a equation that you could solve. But let's be clever. If you make this into y to the power negative m of y prime plus p of x of y1 minus m equals to qx, you would see something. Let's just assume that y1 minus m is a new variable, v. So if you take the derivative of v with respect to y, or with respect to t technically, this would become 1 minus m of y negative m y prime. And so what you see here is that it transformed your equation into v prime plus the 1 minus m that you got of px v equals to 1 minus m of qx. And this is the Bernoulli's equation that you could solve every single time, because there's this very elegant trick. And that's all for the first order differential equation. Now let's talk about the second order differential equation, in which in here we'll just only focusing on the linear type. The second order differential equation. Second order ODE. Let's just do the Frobenius method. So what's the Frobenius method? Frobenius method is just assume the function is a polynomial. Assume the function is a polynomial. And this is like saying that you got your Taylor series going on. So let's try to think of this. Let's say if you have a very specific problem. Let's say the harmonic equation. If you just assume that the solution is a polynomial, your y would be the sum of an of x to the power of n, right? If you just assume this, you could get n and n minus 1, x to the power of n minus 2, plus omega squared an, sorry, there's the an there, x to the power of n, summing them up in n. And that all equals to 0. So this thing will help you to solve the problem now. So if you observe that if the right hand side is 0, this means that the left hand side, everything must equal to 0. So this means that x to the power of 0, so the one that has the x to the power of 0 term, must come from 2a2 of x to the power of 0, right? So it's from the first side plus for the other side, which is n equals to 0, a0, which equals to 0. And you could continue this for, let's say, x1. Let's just do until 1. This would be 6a3 plus omega squared a1 equals to 0. Now, if I want to write this in general, I could just write, let's say, for x to the power of n would be n plus 2, n plus 1 of an plus 2 plus omega squared an equals to 0. Now, an plus 2 over an would later become negative omega squared over n plus 2 and n plus 1. Now you might not really recognize this straight away, but this is a solution of the sine and the cosines. The sine omega t and the cosine omega t, if you do the Taylor series, it has this pattern. And so because of this, you could get the solution that this is just a0 cosine omega t plus a1 sine omega t. This is a very elegant solution of the harmonic equation. So now, instead of looking at the harmonic equation, let's look at something much more quantum mechanical. So we have something which we call as the quantum harmonic oscillator, in which I'll just write this as an equation. So if you know from from quantum physics, you would know about this equation, right? Plus the v of psi equals to e psi. Now, if you solve, let's say v equals to 1/2 kx squared, which is just a potential well for a spring, you could turn this equation into the following. So I won't fully derive how do you do this, but this becomes y double prime minus x squared y equals to negative 2 epsilon y. Now guessing the solution is very hard, but we could solve it by using the Frobenius method. So let's do this. This would be n and n minus 1 of an x to the power of n minus 2 minus x squared an x to the power of n equaling negative 2 epsilon y. Sorry. So it will be just plus then. Plus 2 epsilon an x to the power of n. So if you solve this, let's say if you're interested in the power of n, this would solve into so for x to the power of n, the coefficients will become n plus 2 and n plus 1 of an plus 2 coming from this side, minus from this side it's just x plus 2n, so we could just remove this guy. So this is just an minus 2 plus the term from this final side. And this final side here will have 2 epsilon an. Now what we see here is that there is 3 different terms. And so doing a 3-term ratio is much more harder. Compare that with 2. So we should do something. So you could just set your initial conditions. There's obviously 2 different initial conditions for you to solve, and just assuming that the negatives are just by assuming the negatives are not really existent, so you could just say that to be 0. If you solve for this, it doesn't really help to find a pattern within it. So what you would do is that you would just observe the extremes. And let me show you why that you observe the extremes. Let's just state that the x squared is very small. Very small to the point that the epsilon would be much more greater. So you would get the equation of y double prime equals to negative 2 epsilon y. Now you know about the solution of this. This is just y equals to the sines or the cosines of 2 epsilon t, square root of 2 epsilon t. So you would have this guy and also, oh sorry, this is x. And b cosine square root of 2 epsilon x, right? So it doesn't really help, but it gives you a recognition that when x is very small, this would just become ax plus b. So it's going to be something like linear equation. So now if we consider when x squared goes to infinity, what this will become is the y double prime equals to x squared of y. And this looks like the harmonic equation, but it's not. Because the x squared here is just a function of the y, not a constant. So there should be a solution for this. And there's a way for you to solve such things. And one way is just by literally guessing. So we are just guessing, let's say y equals to e to the power of a integral of f. No, sorry. of f of y, let's say f of x, sorry, because we're just assuming things, and maybe this would brings up into a form of solution. So if you do this, this would become, for the first derivative, this will become f prime of x, e to the power of f x, which is fine. And so for the second derivative, it will become f double derivative of x plus the f prime of x of the e to the power of fx, right? Squared. And now if we consider when x goes to infinity, I'll just assume that this curvature would go to 0. And because if it is not 0, it's just going to curve much more higher, in which in physics, it doesn't make sense, especially for a bound state. So you would get the f prime of x squared e to the power of fx there. And in here, based on the differential equation that we hope to solve, we'll get something like this. So our guess is f prime of x would be x. And a good solution of this is f equals to x squared over 2. So now we could start from here, and maybe we could guess some solutions. So this is a plus minus, sorry. So this will be plus or minus x squared over 2. So now what we observe is that at the endpoints, our solution is hopefully e to the power of x squared over 2. Well, a constant multiplied by e to the power of x squared over 2. And then the left-hand side, and then you also multiply this by something in which if it goes to 0 is a linear equation. So we could just guess a solution. Maybe u e to the power of x squared over 2 could be a solution. Let's just assume that this is negative, because if it's positive, x squared over 2 will just blow up. So we'll just choose negative x squared over 2. And maybe we should try and plug this into our equation. So let's just do the same problem. So if you put it into your differential equation of y double prime minus x squared y equals to negative 2 epsilon y, this would be transformed. So if you put this in, you would get the, let's see here. So you would get the u double prime e to the power negative x squared. Oh, sorry. Let's just do it one by one. So the first derivative of y would be the derivative of u e to the power negative x squared over 2 plus u of the negative x e to the power negative x squared over 2. And the double derivative would become u double derivative of e to the power negative x squared over 2 minus the u derivative of x e to the power negative x squared over 2 plus, minus the u prime of x, and also, so it's xu, so it's just u of e to the power negative x squared over 2. Sorry. And this thing is multiplied by x. No, sorry. You also add this with the u of x of negative x, so it's negative x squared there. E to the power negative x squared over 2. So if you simplify this, this becomes u double prime of negative 2u prime x minus u plus ux squared e to the power negative x squared over 2. And so this is just some derivatives, right? And so if you now put it again into the differential equation, just by substituting this, you would get u double prime minus 2u prime x minus u plus ux squared. And we'll just factorize off the e to the power negative x squared over 2. And so you would also have the minus x squared there of the original function, so it's just u. And this would equal to negative 2 epsilon of the u e to the power negative x squared over 2. And these two things cancel. So what you would get is a new equation, u double prime minus 2u prime of x plus 2 epsilon minus 1 of u equals to 0. So now you could solve this new problem, in which this is another second order differential equation, but let's just do straight away the Frobenius method. You would get the n minus 1 of un x to the power of n minus 2 minus 2 of, so it's x, that means it's n, un x to the power of n minus 1 times x, which is n, plus 2 epsilon minus 1 of x to the power of n un equals to 0. And now we're lucky. We see that it turns out that if you just check for the coefficients of x to the power of n, you would get n plus 2 and n plus 1 of un plus 2 minus 2n of un plus 2 epsilon minus 1 of un, which means that you could get the ratio now over un, which is just, let's see, the bottom side will be n plus 2 and n plus 1, and the top side would become 2n minus 2 epsilon plus 1. And this is the ratio. Now, if you check the limit as n goes to infinity, you would get this to be like 2 over n. And this is a very suspicious thing to see. So now let me show you why this is very suspicious. If you just compare this with e to the power 2y squared, this was, so if you just do the sum, it's just 2y squared to the power of n over n factorial, right? And if you do the ratio test, but checking the n plus 1, you'd get the 2 there, and then, so it's the 2n plus 1 over n plus 1 factorial over the 2 over the n, right? N factorial. And this turns out to be just 2 over n plus 1, which is very closely related to the 2 over n that we got here. So it's gonna guarantee blow up if you got the e to the power negative y squared over 2 that we have already tried to put in for protection. And if you have this thing to be unluckily a value that blows up to infinite when n goes to infinity, it becomes e to the power 2y squared over 2, which means that it will later blow up if you go further out. So it's a very big problem. And you could solve this. You could solve a method for you to make sure that it would blow up at the edge. And one of the methods is just by having one of the ratios to be equal to 0. And it is because if you later have the ratio to be equal to 0 for one of them, the next ratio going upwards would be just the un plus 2 times something that is 2 over n, right? But you multiply it by 0, which will later conclude to a 0. And this is where quantization comes in. So, how do you make sure that this coefficient at one period of time would equal to 0? 2n equals to 2 epsilon minus 1, or n equals to epsilon minus 1 over 2. And because n is an integer, this quantization would conclude that epsilon is n plus 1 over 2. And this is where the quantization of a quantum harmonic oscillator comes in. It's coming from this boundary condition where you couldn't have it blow up. So if you add this condition straight away, you could solve for something which you call as the Harmonic polynomials. And I will just solve 4 of these. So let's start with the very first one of h0. So for h0, you could just get it straight away just by looking at the ratio. u2 over u0 would equal to, the epsilon would be half, right? So it's just going to be 2n over n plus 2. So 2n would just straight away resolve to a 0. So this is just u0. And so for the Harmonic polynomials, the u0 is normally written as another number, which is written as a certain convention which I don't fully know, and also it's not really that important to know. So the first Harmonic polynomial is just u0. For h1, it's just u1, because u3 over u1 of 3 over 2, just put it in. So it's 2n minus 2, and for n equals to 1, it equals to 0 as well. This is for h0, h1. Now for h2, you would need to consider u2 over u0, which would be this would become a 5 over 2. So it's, yeah. So the 2 epsilon minus 1 would become, uh, yeah, so the 2 epsilon minus 1 would become a 6. So it's 2n minus 6 over n plus 2 and n plus 1, right? No, sorry, negative 4. My bad. And so for u2 over u0, this would become negative 2. And then for u4 over u2, this would be 0. So it's just, so for h2, it's just u0 of 1 minus 2x squared. There you go. That's the second Hermite polynomial. And for h3, you could use the same idea. This would equal to 2n minus 6 over n plus 2 and n plus 1. Plugging in 1, the bottom side will become 6. The top side would be negative 4. So it's negative 2 over 3. And then going to u5, it's just a 0. So it's just u1 of x minus 2/3 x cubed. Something like this. And so this Hermite polynomial is the solution of the quantum harmonic oscillator. Multiply that by e to the power negative x squared over 2. And also, these Hermite polynomials are orthogonal, especially if you already multiply it by e to the power negative x squared. So it's a very useful set of bases, especially if you're doing a quantum harmonic oscillator. Another type of equation that you normally visit in terms of in quantum physics is the Legendre polynomial. So this Legendre polynomial is a solution of the orbital spin, or the spin of the electron in itself. And so the equation is 1 minus x squared y double prime minus 2xy prime plus L and L plus 1 y equals to 0. So these L's will later be quantized thanks to the quantization. So yeah, it's the same idea in which it will later blow up when it goes to infinity. So you want to preserve that, and it turns out that the way for you to preserve such function is just by taking L to be integers. And so this is the general polynomial or equation. So we mostly discuss about the Frobenius method straight away, but let me just show you a very particular example in which x squared y double prime plus xy prime plus x minus 2 y equals to 0. And let me show you a problem. If you just solve this straight away, x bar n plus 2, sorry, it's just n, and also x to the power n as well. And in here, it's going to be x to the power n plus 1. So of this is un, sorry, my bad, I forgot. Minus 2 un of x to the power n equals to 0. So if you check for x to the power n here, the ratio would become n minus 1, and un plus un plus un minus 1 and minus 2 un equals to 0. Now if you solve for this, for the ratio un over un minus 1, this would become, let's see, it's a negative of 1 over n squared minus n plus n. Okay, so it's canceling each other out. Minus 2, n squared minus 2. So now if you check this and start with the u0, which is the relation of negative 1 over negative 2 times the 0, right? Because un minus 1 for 0 is u negative 1, which is 0. It results into another 0, right? And this is dangerous because going upwards now, everything becomes 0. So there's no solution. The only solution is 0. So this doesn't give you a good solution. So instead, what you would do is that you just multiply this solution by x to the power of x. x to the power of s. So if you just do this instead, this would give you a solution. And let me do this for the xn to power x power of n plus s. And so the coefficients will become n plus s minus 1 of un plus n plus s of un plus un minus 1 minus 2un equals to 0. So if you take the ratio now, what you would get is it's going to be the negative 1 over n plus s squared minus 2. Now, if you want, so let's say if the n equals to 0 now, u negative 1 would be 0, right? And so the way for you to make sure that u0 is not 0 is if this is 0. So n plus s squared minus 2 has to be 0, especially for when it's 0. So your s would be plus or minus squared 2. And now if you plug this into your solutions now, you would get the x power negative squared 2 of your an's, x power of n, and x squared 2 of the bn of x to the power of n. And this gives you the two solutions that you need. And so in here, what I've shown here is that we have something which you call as the initial equation, and this is the one that is referring to the ratio. Now this initial equation tells you where does the power starts. And so it turns out that if you actually just solve a second order differential equation of, let's say, y double dot plus p of y dot plus qy equals to 0. I'm sorry, it's technically something like this if you write it as this, because this is where the singularity normally comes in. It would have something like this form, right? So if the s1 is not equal to s2, you could just simply do this thing here, and the sum is just the solution. It's pretty simple because if you know already, if one thing is a solution and another one is a solution, summing them both will also become a solution. The second thing is that if s1 equals to s2, this is a very problematic case, but the same thing that you did with the first order differential equation, you could just take the d over ds of this x to the power of s of the sum of an x to the power of n, which is the an is a function of s. And so if you do this derivative, you would get the first part would be just become the natural log of x to the power of s of the first solution, y1, plus the x to the power of s of another set of equation. So b and f x over x to the power of n. And normally this thing here is the same. So this is normally the same. But it could be different. So there are some examples that has this bn the same thing as an, but it could be different. So this is why we have different notations of the an and the bn. But you could solve the bn as well just by putting this theoretical solution back into your differential equation to solve for each of the bn's. And this is the sorry. So there shouldn't be anything of this. So it's like y1 natural log of x plus x power of s of the sum of the bn of s. And this is the general solution if the indices are degenerate. Lastly, there is another condition in which s1 minus s2 is a natural number. And let me show you one of the examples of this thing existing, and it doesn't give you a very good solution, which is the Basel's equation. And the Basel function is pretty much the solution of anything which has a spheric, a circular symmetry or radial symmetry, which I will later show. But for now, I just want to reveal I just want you to reveal. I want to show you the equation first, which is x squared y double prime plus xy prime plus x squared minus v squared y equals to 0. Now, if you do the indices again, this would become n plus s minus 1 of xn plus s plus the n plus s of the xn plus s plus the xn plus s plus 2 and the minus v squared of xn plus s, everything of the un, okay, equals to 0. Now if you refer to the coefficients of the xn plus s, this would become the un of n plus s of n plus s minus 1 plus the un of n plus s minus the v squared of the, minus the v squared un plus the u of n minus 2. And this must equal to 0, right? So this would be simplified further into something like this, minus v squared there, which is equal to the negative un minus 2. Now, if the n equals to 0, this would be 0, right? u0, and so this thing must be 0, s squared minus v squared. So the s is plus or minus the v here. Now, something that I want to show is that obviously if you have the v to be a rational number or a irrational number, it's totally fine. But when it comes to the v to be a natural number, something weird starts to happen. Let's just start with the x squared negative of the natural number nu. So let's start with the s equals to the negative nu. If you solve the problem, what you would get is that un of the n squared plus 2n, negative 2n nu must equal to the negative un minus 2. And so this would mean that the un of n times n minus 2 nu must equal to the negative un minus 2, closed. So now if you consider when s equals to negative nu, what you would later observe is that the entire equation will become just the n minus nu squared minus nu squared equals to negative un minus 2, right? So this would become the un of n times the n minus 2 nu equals to negative un minus 2. Now this is what literally makes it weird. You observe here that when the n equals to 2 nu, so now what happens when n equals to 2 nu? If you solve for the solution when it is 2 nu, this would become negative 1 over 0, which is not possible. So this means that this part should be 0, but which also means that going downwards, everything should be 0. So u0 couldn't be 0, couldn't be a non-zero. This is something that you observe. So the only solution where it starts is when it is at u2 nu, which is starting from x nu if you just already multiply with x squared negative nu. So this is like as if that it is acting with s equals to nu. And this is something interesting about the Basel function. And there's a property of the Basel function that is normally written as the order would be the negative 1 to the power of n of the negative n of x. So it turns out that the Basel function of the order negative n is just proportional to the jn of x, which means that it is not linearly independent. So this drives into a way for you to solve such problem in which you instead of doing x to the power of s, the sum of an of x to the power of n, for your first solution, your second solution would be guessing another solution, which is a natural log of x of y1. And then you take this second one, the sum of bn x to the power of n. And now these two things will be related to each other. And also, you could later solve the a as well as the bn from this new equation. And even though if you couldn't really make it into one single constant for the bn as well as the a, but it turns out that you could write them in terms of another proportionality with y1. And later the linear combination would later become the general solution. And so therefore every single dependence of this y1 will just be combined into the constant of y1. And so this is why the y1 and the y2 are literally orthonormal to each other because of this proportionality technically. So what's the second solution of the Basel's function? The second solution is something which you call as the Newman's function, in which I won't fully discuss as well. But the Newman's function is the solution of the Basel function when nu is a natural, but it's the second solution of it, which is normally written as nn of x. And it's the limit when nu goes to n of the cosine pi nu of j nu minus j negative nu over sine pi of nu. That's the solution. And so I won't fully derive why it is like that, because it's much more mathematical to what this course really wants you to learn about. Finally, we can talk about the partial differential equation, or the PDE. So the PDE is sometimes very hard for you to solve. It's sometimes even impossible for you to solve. But when it is linear, you could do it. And there's a very popular way of you doing it. So let's just observe the wave function. Wave function is like this: partial t squared equals to partial squared psi over partial x squared. A very elegant way to solve a partial differential equation is by separation of variables. So you just assume psi equals to x of x and t of t, in which each of these functions are functions of the variables independently. So if you plug this in, you would get the 1 over v squared of partial squared psi, partial squared t over partial t squared, where x is out, and partial squared x over partial x squared, in which t can go outside. And now if you divide both sides by x over t, you would get 1 over v squared 1 over t partial squared t over partial t squared equal to 1 over x partial squared x over partial x squared. Now here's something that I want you to realize. If the left-hand side is a function of time and the right-hand side is a function of position, they have to be a constant. And you could just write this constant as anything. And here I will just write this as negative k squared. And let me tell you why. If you observe this second part here, and if you do negative k squared, the solution is very obvious. X equals to the cosine of kx, and same thing for the sine as well, sine kx as well. A and b, right? And then the t could be solved again. The t would just become a sine vkt, and let's just do c and d cosine vkt. It's that simple. You could also do this for higher orders of partial differential equations. Like maybe it's instead of one-dimensional wave equation, it could be a second order, in which it is written like this: lambda squared of psi. And separation of variables could tell you that psi equals to xyt. So the solution would become 1 over v squared partial squared t over the partial t squared, and some other random things which is a function of x and y. And this could later be resolved into the k squared, and then later this thing here would be related with this negative k squared. And what you could do is that you could separate those two things into two different variables. You could state one of them is negative kx squared and the other one negative ky squared. And if you do this independently, what you would get is the wave equation both in the x and in the y direction. and it will just solve the equation. Now, something that I want to highlight about this is that even though something that I want to highlight from this is that solving this in this manner, just by assuming the solution is just some sines and cosines, it's just some Fourier series of a certain function. And so you could take a initial condition, which is a function normally, and 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 then if you do the Fourier series, what you could do is that you could just sum up each of these independent solutions into one that it also follows this partial differential equation. Let me show you another type of the wave equation, but instead of looking at this in the Cartesian form, let's observe this in the polar form. So it can be converted into 1 over r, partial over partial r, of r, partial psi over partial r, plus 1 over r squared, partial squared psi over partial phi squared. And so if you do the separation of variable, r, phi, t, what you would get is that this would be 1 over v squared t partial squared t over partial t squared is equaling the right hand side, which is 1 over r partial over partial r partial r over partial r, and if you just, and the phi t goes outside, and then dividing everything by the psi, the r becomes at the bottom, and the same thing here, 1 over phi r squared partial squared phi over partial phi squared. Now, because of the left hand side is just a function of time, and the right hand side is not a function of time, this has to be a constant, which I will denote as the negative k squared again. And now the negative k squared here, if you take this for the time, this will just become the sine vkt or cosine vkt. So there's the a and the b for the integration constants. And now for this side here, if you try to convert it again, just multiplying both sides by r squared, just to make sure that this side here doesn't have any function of r, what you would get is r over r, partial over partial r, r partial r over partial r, plus 1 over phi squared, phi partial squared phi over partial phi squared, plus k r squared equals to 0. What you could conclude is that this thing here could be negative m squared. And it turns out that if you actually solve this, the phi should be the sine of m phi, right? But I'm sorry, this would be e to the power I m phi. And here's something that I want to show. This m here must be an integer. And it is an integer because of rotational symmetry. And so this will later impose another variable inside of this equation, which becomes r over r partial over partial r, r partial r over partial r, the minus m squared plus k squared r equals to 0. Now this thing here, if you don't already recognize this is the basal equation. So if you just transform kr into your x, this would just become into the basal's equation, the basal function now. So the solution is the basal function. And now there's something that I left hanging on General Physics 1, in which if you have the circular aperture and then you want to find the natural frequency, what is the natural frequency? And if you take the boundary to be a, and then put it into the very first basal function, and if you do the numerical integration or numerical computation, what you would get is the value here is the 2.4 that you get. So another thing on partial differential equations is the heat equation. The heat equation is also something that's pretty popular when talking about partial differential equations. And it's just the partial u over partial t minus the Laplacian of u equals to 0, in which u is just your temperature. So you could also solve this by using separation of variables, and And that's pretty much all on partial differential equations. The final chapter that I want to talk about is about the green function method. So the green function method is a very particular method for you to solve a differential equation. And the way that you do it is by, so let's just do an example. If you have negative partial squared plus m squared of, let's say phi equals to rho over epsilon 0. So this is just the, so this is what we call as the Poisson's screened equation, in which it is describing a charge screened by something, in which it is having the factor of m here. So the Green's method is a method that you just take a particular. So the Green's method is a method in which it is a function that if you plug it in will result into the delta function. Now, why is this essential for solving such things? So what exactly the Green's function does is that it is the contribution of one particular part of the differential equation. So what does the Green function actually mean? The Green function is just the function of a particular effect at a certain point. And and you want to relate this in general. So if you take all of these small contributions and then you sum them all up, you would get the solution of the differential equation. So I won't fully discuss about how do you use the Green's function here, but if you want more discussion about the Green's function method, you can just leave it in the comments for the discussion on the Green's function. And so that's all for and so the time for me to prepare this video is quite long, that I need to study for it first, and maybe I don't even discuss most of it. And so if you want more discussions about a particular topic, you can just leave it in the comments. And this is the end for foundational mathematics for science and engineering. And so thank you very much for watching, and make sure to like and subscribe. And also, please share this to your friends who really need to understand the mathematics behind physics in a much more deeper understanding. This is Understanding Physics, and I will see you on the next course.